So, here we are going to look at the last chapter, a simulation chapter on molecular dynamics. We have already looked at one of them called the Monte Carlo, and this is the other one that we see called as the molecular dynamics. So, let us give a short introduction of what molecular dynamics is and how the simulation etcetera are carried out, what is it based on, what are the pitfalls and what are the advantages and so on. And we have already said this, the first slide is just for repetition and to remind you that why simulations are important. The computer simulations are of course carried out with the expectation of understanding properties of molecules or a large number of particles which are interacting with each other via macroscopic interactions between them. Okay. So, they are talking to each other or they are interacting with each other by certain potential, the form of the potential or the force involved will have to be decided by the nature of the system or the nature of the particles. If you are talking about an atomic system, there will be some kind of force, or if they are talking about molecular system, you are talking about a different kind of force. And if you are talking about matching with the spectroscopic data, then we might really need another kind of force and so on. Okay. In either of these cases, we may have an external field that is present or an external potential that could be present. It is not necessary for that. In fact, we would leave it out of our discussion of having an external field or a potential to be present, but nevertheless it could be there and it does not harm the simulations in any way. This serves as a complement to conventional experiments which we have discussed at length, that sometimes performing the real experiments can become very hazardous and can become very expensive in terms of the resources, the computer resources or the manpower that is involved, or it could be also very expensive in terms of the time. Which could take even months and years of simulation in order to find a certain conclusion for a given problem, whereas these experiments, the computer experiments can be performed without having us to spend that much of time, and the results also can be analyzed in within a reasonable time. The simulations are likely to yield something new. What I mean is that sometimes some correlations, sometimes some physical properties which are not directly achievable in experiments. So, that way simulations have a lot of value and we have seen that earlier. Having seen Monte Carlo, so why do you want to see molecular dynamics? And the reason being that the simulation methodologies usually come in two flavors, one being the stochastic and the other is the deterministic. So, the stochastic modeling that presents data and predicts outcome with certain levels of unpredictability or randomness. We have seen this. We have taken a set of data points which are taken from a known distribution, but random points. These are random points being taken, and if you take all the random points with equal probability, then we see that it is a normal distribution or rather a crude Monte Carlo, whereas if we take them with certain bias, however the bias actually goes away as the number of points become too large. And these are seen in the Monte Carlo technique that we have seen, and the Monte Carlo technique actually falls in this category of stochastic modeling. So, this is one word that we are coming across which we have not mentioned. This is to distinguish what we are going to learn here on the deterministic modeling, that is another class which yields the same exact results for a particular set of inputs, and no matter how many times one actually recalculates the model. So, you are going to get the same set of output every time you give the same inputs, and that is not the case with the stochastic modeling. You are likely to get different, slightly different maybe, and there is an unpredictability for the Monte Carlo technique. This is called as the molecular dynamics. So, molecular dynamics fall into this category. So, what are MD simulations. So, Monte Carlo is abbreviated as MD, and this is done everywhere. So, it is MD simulations is a very common colloquial word used in this particular context. So, the basic idea of MD is to explore the behavior of a physical system by computing with significant accuracy the trajectories of individual particles constituting the system. So, you have a large number of particles, and these particles are interacting with each other through certain potential, okay, which could be Coulomb potential, which could be some other kind of potential. As I said, that one can have an external field which or an external potential, but that could be sort of skipped at this moment. In the course of the computation, relevant information about the system is accumulated. Okay. So, the particles are moving, they are not stationary, they are made to evolve according to certain equations of motion. Now, these equations of motion are to be solved pertaining to certain conditions or boundary conditions, as we have learned, and these differential equations will give us finally the trajectory of the particle of the system rather, which is a set of particles, not a single particle, but a set of particles which have an interaction between them. Previously, for studying these other the initial value and the boundary value problem, we have always talked about just one particle or one sort of entity of the system, and wanted to see that how it evolves with time. Here we in addition to that, we have a large number of particles, and these particles are interacting with each other. So, we want these information to be calculated as physical quantities, which come out as statistical averages along the trajectory. Okay. So, the formal basis of why MD works for different problems of statistical mechanics is the what is called as the ergodic hypothesis. There is a concept that is very common or fundamental to statistical mechanics. So, what it says is that the ensemble average of a system is same as the time average. So, a time average can be actually replaced by the ensemble average. Let us see what we mean by that. Suppose you have a gas, an ideal gas, say, which has is in a volume, say, which is there are these particles constituting the gas, and there is certain pressure, volume and temperature of the gas, and the pressure occurs because these molecules of the gas is continuously exerting pressure or colliding with the walls of these irregular shaped boundary that we have considered, and volume is the volume of these irregular shaped boundary that we are talking about, and temperature comes out because of the kinetic energy of the molecules. Okay. So, this is the equipartition theorem says that per harmonic degree of freedom, the kinetic energy or the energy, total energy is per degree of freedom is at thermal equilibrium equal to half kT. Now, the particles of the gas are of course moving, and they are interacting with each other. They could be interacting via some really complicated potentials, or they could only be interacting with each other when they meet each other. That is they sort of move or flow as non-interacting particles, and then they sort of undergo a solid sphere or a hard-on collision, elastic collision, and then they change their directions, and sort of this is goes on in the system. So, as the system you wait for the system to evolve, the system comes with a different configuration if we are able to identify the molecules or the atoms constituting this gas somehow by either coloring them or naming them, then we will find a different configuration at every different instant of time, in which case the pressure, volume, temperature, etc., or other physical parameters, they would be functions of time. And this is what again goes against the spirit of equilibrium stat mech, where we actually, when we talk about a pressure or a volume or a temperature, these are often the, or rather these are always the equilibrium quantities, and they do not depend on time. Now, in order to have these that they can't be, we cannot quote things which are functions of time, yet we want their equilibrium values. So, this ergodic hypothesis is proposed, where it says that let me make several mental copies of this system. So, this is the system of an ideal gas at a given some pressure, volume and temperature and so on. So, if I make several mental copies of this gas and say that, and they are called as ensembles, so that we understand that as time progresses, if we make really large number of these ensembles, then the gas or rather the system would actually visit some ensemble or the other during its course of evolution. Okay. So, which means that we are making an assumption that our system is actually traversing or visiting all these different ensembles or the mental copies that we have made of the system in our mind. And then if we wait for long enough and kind of assume that the system has visited all the mental copies or the ensemble, then instead of taking a time average, we can take an ensemble average. So, taking a time average and ensemble average would be same, and we would get, by taking this ensemble average, we would get the equilibrium properties of the system, and then there is no time dependence. So, this is called as ergodic hypothesis, and the Monte Carlo simulations, they crucially depend upon this hypothesis. So, as I said that instead of time averages over very long paths, the ensemble average for different physical quantities are done. Okay. Here we shall really study the most rudimentary version of this MD simulation, because it is not really a specialized course, it is a course which gives you an overview of the different numerical techniques. So, we will restrict ourselves to constant energy and constant number of particles, and if you are aware of statistical mechanics, or if you have learned statistical mechanics at the undergraduate level, then you know that this corresponds to what is called as a microcanonical ensemble. And in a canonical ensemble, the system is actually is put in a thermal contact with a temperature bath. Temperature bath is an object which even if you or that is in contact with the, when it is in contact with the system, the system can exchange energy with the bath. The temperature of the bath does not change, but finally the the system comes in equilibrium with the bath by exchanging energy. Okay. And this is called canonical ensemble, and when you also relax the constraint of keeping the number of particles to be same, that is called as a grand canonical ensemble. All right. So, just give you an example, say this room is very big, and I have a cup of tea in the on my table, and I want to drink it, but since it is a little hot, I can't immediately drink it or all of it, and I keep it on the table. Now, as the time progresses, the tea will become colder and colder, but the temperature of the room does not rise. So, the whole room is like a temperature bath, and the tea is like our system, which is which could be an ideal gas and so on. So, these are some ensembles that one talks about. As I told, that there are three of them. One is called as a microcanonical, which is already said, and then we can have a canonical ensemble, which talks about exchange of energy, and there is also a grand canonical ensemble, which talks about exchange of the number of particles. All right. So, we will restrict ourselves to the simplest case, which is for a given energy. So, the energy is same, the number of particles is same, there is no bath. So, the system cannot exchange energy with a bath. So, it is an isolated system, so to say. Once again we reiterate that this is really very rudimentary introduction of the subject, and there are lots of specialized references, not only the 5 that I have listed, but very large number of them, and one can go through this if one is interested, or one takes it up for further specialized studies. They are these Rappaport's book on the art of molecular dynamics simulations, or Hale on the molecular dynamics simulation again, Frankel and Smith understanding molecular simulations, Maitland et al. On the intermolecular forces, their origin and determination, and Duffel-Hard on the computational molecular dynamics challenges, methods and ideas. Okay. So, these are very brief introduction of the subject. Now, let us get into the details or rather the technical details of this particular topic of molecular dynamics. So, what we have to solve is what are called as the equations of motion. So, we need to generate trajectories for a given system of particles, and in short this is called as a EOM. So, the MD aims to numerically integrate the equation of motion of n interacting particles. So, the EOM is written as Mi d2 Ri dt2 equal to Fi, where I equal to 1 to n. Now, remember this is called as a Newton's equation of motion. All of you are familiar with right from maybe class 6th or 7th or 8th maybe. However, this is not the only equation of motion that we know. We have Lagrange's equation of motion, we have Hamilton's equation of motion, and so on. Lagrange's equation of motion is a second order, whereas the Hamilton's equation of motion is a first order equation. So, anything would do, but we are mostly familiar with this. So, we are starting with this as a equation of motion, and we have n particles, capital N is a number of particles. So, let us just remind you saying that the Lagrange's EOM and Hamilton's EOM are possible. So, Fi depends on the positions of the particle. It can depend upon other things, but let us just talk about only positions of the particle and ignore velocity dependent forces. So, when you have velocity dependent forces, when you have a damping term, or if you are talking about a charged particle in an electromagnetic field, that also has potential or rather the force of course depends upon velocity, and so there are complications there. So, we ignore these velocity dependent forces, and so these the positions of the particles are given by R1, R2 and Rn. And third is that assume no external forces are acting on the system. Okay. So, these are the main feature of what we want to do. So, this is the equation that we want to solve, and as I said that this could have been solved even otherwise by in the spirit of solving just a differential equation, but now imagine that there are these interacting particles and this interaction has to be taken into account. Okay. So, we can talk about different kind of potential, and a few potentials that we are going to consider is the following, which is mostly there for molecular interactions. So, one is called as a Lennard-Jones potential. And for charged particles, one can have a Coulomb potential. And the vibrational spectra of atoms, they can be described by what is called as a Morse potential. Okay. We will see briefly what they are, mostly going to talk about Lennard-Jones potential. So, let us write down Lennard-Jones potential. So, consider a system of particles interacting with each other via Lennard-Jones potential. So, V R1, R2, R3, etc., Rn is takes a form where I equal to 1 to n, j equal to 1 to n minus 1, just leaving that one particle, and then there is a V R I j, and where V R I j takes a form 4 epsilon. This is very conventional to write it this way. It is a sigma by R I j 12 minus sigma by R I j 6, and this is called as a 612 potential because of these powers 6 and 12, where R I j it is equal to R I minus R j. So, that is the distance between I and j. It only depends on the distance and not the individually on this R I and R j, and so they denote distance or magnitude of the distance. I and j, and so if you actually plot this, it takes a form is more like it. So, this is your V of r and this is r. So, I am writing that R I minus R j for a moment as r. So, this one is written as r, and so this is the form. So, what it says is that it is very strongly repulsive at short distances and very weakly attractive at large distances. Okay. So, this is the form of the potential. This is the distance, the unit of distance is sigma, and this is a particular point. We will find out what this, write down this as something like a sigma star or some such notation that is given here, this has a depth of epsilon, where epsilon is the one that it appears at the as a coefficient of these bracketed term. So, there is 4 epsilon. So, this is that and this is the distance. So, at as r goes to 0, as the two molecules they come very close to each other, there is an enormous repulsion, and as they go away from each other there is a weak, very weak attraction, and this attraction asymptotically vanishes when the distance between the two molecules that become very large. So, let us see some features of this potential. So, let us just write it as Lj. So, Lj potential, Lennard-Jones. So, it has a pairwise additive form. What we mean is the following, that there are two sums I and j, and this is pairwise additive, and so these two additions are referred to as being pairwise additive. So, it depends on the positions of the particles. Only through n into n minus 1 by 2. So, there are you are summing over really n of those particles, pairwise distance. So, this is a number of pairwise distances. R I minus R j, which is of course equal to R I j. Okay. The sum of n numbers is n into n minus 1 by 2, and so these are n particles. So, this form of the potential depends upon these many number of n into n minus 1 by 2 numbers of pairwise distances. It obeys translational and rotational invariances. Okay. For any pair of particles, why translational? Because it is R I minus R j, and because it is a magnitude, even it is rotationally invariant. Okay. So, even if you rotate the system, then it does not matter, because it is just the magnitude of the distance. So, there is no angle involved, etc. For any pair of particles, the potential has a shallow, we have not of course quite shown it as shallow, but it is a shallow minimum at a distance sigma star, which is equal to 2 to the power 1 by 6 sigma, which is equal to 1.122 sigma. So, this is the equilibrium distance of this. So, this is called as the equilibrium distance. And this has a value which is 1.122 times this. I have of course shown it with a lot of over exaggerated it, but this is not too far away from this, and it is a very shallow potential, which I have shown it as a lot of depth because of to show these distance and all that. 5 is for distances lesser than the interaction is sharply repulsive and for sigma to be greater than sigma star, the interaction is weakly repulsive, sorry, weakly attractive. So, a very important thing here is that the energy and the length scales are 4 epsilon and sigma respectively. So, let us write down certain values for the noble gases. So, this is an example. So, gas, so this is helium, neon, argon, krypton and xenon. Okay. This is epsilon in Kelvin, this is sigma star in angstrom, and this is m, this is in not in grams, this is in mu, and finally the density which is in gram per cc. Okay. So, this is 10.80, this is 36.68, this is 120.0, 171.0, 221.0, where the sigma stars in angstrom are 2.57, 2.79, 3.38, 3.6, 4.1. So, it is between 2.5 to 4.1 in for these cases, and the masses are 4.002, 20.180, 39.948, 83.800 and 131.290. Similarly, for the densities it is equal to 0.179 in gram per cc, 0.901, 1.784 and 3.740, 5.897. Okay. So, it is important to see that for the Lennard-Jones potential, the corresponding force which is given by let us call it FLJ, which is equal to minus grad VI, or we decided to write it as okay. So, on a given, so this is, and this is like R1, R2, Rn on the ith particle is given by. So, let us write, let us swap this things here. So, let us write Lj here and the I here. Let us just drop this Lj for the moment and then write this as R1, R2, Rn, and this is equal to j not equal to I. So, this is not equal to I can be j, which is not equal to I, equal to 1 to n f r I j and r I minus r j, okay, where f r I j, this is equal to 6 4 epsilon by sigma square 2 sigma by r I j to the power 14 sigma by r I j whole to the power 8 and so on. Okay. So, maybe a note on the units for this simulation. So, using conventional units for this simulation, MD simulation is actually inconvenient, because one is that the numbers could be so small or so large that it will introduce difficulty for the computers to handle those numbers. And that is the reason that one has actually come up with natural units for these. So, we have 4 epsilon is the unit for energy, sigma for length, and m for the mass. Okay. And remember that this is the equation of motion that we have talked about. So, this mass is important, and so if you are given a simple problem that what is in a Lj potential if 4 epsilon equal to sigma equal to m equal to 1 is set. So, this is are set to 1, what is the unit of time? That is the question. Okay. So, we have 4 sigma equal to sorry, not 4 sigma, it is 4 epsilon equal to sigma equal to m equal to 1, and time is then in root over m sigma square by 4 epsilon. Let me tell you how, because energy has got say we just talk about potential energy, which is mgh. So, m g is acceleration due to gravity. So, we will write it as m L t minus 2, okay, because length by it is meter per second square. So, it is that is the way it is L t minus 2, and h is again length. So, we are talking about mgh, nevertheless you can take half mv square also, does not matter. So, finally, you will land up with a m L square t to the power minus 2, all right, and we want t. So, we have a t square here, which is equal to m L square by E, and so t is equal to root over m L square by E, and this is equal to m is m, L square is sigma square, and E is 4 epsilon, and that is how it is m sigma square by 4 epsilon. Let us quickly look at 2 more potential. So, we have Coulomb potential, which we are very familiar with. So, if one has charged particles, then one for electrostatic charges, one can write down a Coulomb potential which is of the form of V Coulomb R I j, again for the pair of particles q I q j divided by 4 pi epsilon 0 R I j, and again R I j it's equal to R I minus R j. So, again it depends on the distance between the two particles, and the q I and q j are the electrostatic charges. So, this is a different kind of potential than what we have already seen. It is of course a falls off asymptotically, and so this is a V Coulomb and function of R. So, it is actually strongly repulsive at short distances and becomes weakly repulsive at large distances. And let us also look at another one called as a Morse potential. So, it is important for the vibrational spectra of atoms. Okay. So, what happens is that you can have the vibrational spectra as well from the harmonic oscillator potential, but this is better than the harmonic oscillator potential in terms of having an anharmonic term. So, there is an anharmonic term being present, and the Morse potential is written as V r equal to some d E 1 minus exponential r minus r e whole square. So, r is the distance between the atoms, r e is the equilibrium bond distance, d E is the well depth, and A controls the width of the potential. So, one can actually talk about, so this is your, so this is d E, which appears as a coefficient of this term. So, this is V of r and versus r. So, see that there is an anharmonic part there. So, this is R e, and also one can get a force constant, which is the you know, the elastic modulus of the atoms, can be obtained by a Taylor expansion about r equal to r e. Okay. So, these are the different potentials that one can talk about for which would generate a force field which gives you an interaction between the particles, whether they are atoms or molecules or something else, and then one can solve the equations of motion with some conditions, and we will see the details of the solution according to certain algorithm in the next discussion.